a bit simple for most of the parts of the talk, but for all of you may find interesting even from the beginning. So please reach your level through the talk. As you may know, you already saw from the lecture yesterday, we have different calibration steps to conduct in VLBI data. This is a list of the common ones that should be applied in AVN datasets, for example, like from the parametric angle correction that was mentioned yesterday, and simple ones. Some of the calibrations are exactly the same, not only for VLBI, but almost for any radio data analysis, like the bandpass calibration, and of course, cleaning and self-calibration. And there are some of them that are really particular for VLBI, like the a priori gain calibration, so how we apply the system temperatures, as you had a discussion yesterday and also in the chats, and the fringe fit. In this talk, I'm not going to focus in the really details about the basics of each of these ones. I will explain why and the concept of them, but then you are going to have different and focused lectures on each of these steps. So again, I'm not going to discuss the really fundamentals of radio interferometers or radio analysis. I'm just showing the concepts to be able to understand them. But of course, we will need to, or it's helpful to start with a few slides from the very beginning to understand. If someone is interested on the really details and fundamentals of those ones, you may find this book that is actually freely available to download. So everyone can watch at it, and it's a good reference textbook for radio analysis. So again, here we are playing with interferometers, which means that we are combining the signal from at least pair of antennas. And of course, we want that because we can reach a higher resolution. If we combine coherently the data from two different radio antennas, then the resolution that we can achieve is inversely proportional to the separation of these two antennas, which means that, for example, for antennas that are separating of the order of 1,000 kilometers, we can already reach resolutions of the order of the millisecond at gigahertz frequencies. Okay, so that's the fundamental basics of purposes of VLBI interferometers. Here in-house, we have the AVN, which is currently the largest VLBI network in the world, and also the most sensitive at gigahertz frequencies. And basically, we're combining data from antennas that are basically in Europe, Asia, South Africa, and Central America. So again, if we really want to combine the data coherently from each pair of antennas here, we really need to trace and make a geometrical model on where they are placed and what we are observing. Basically, each of the antennas will receive the signal from a source in the sky, and then we really want to combine coherently. So that means that we are combining the same wavefront at the same particular time. That means that we need to take into account the geometrical delays. Here you see the wavefront coming from the source. So you need to take and remove the geometrical delays that you may have in the signal as it arrives to one on another station. And this, of course, involves knowing with high precision, at least to the precision proportional to the wavelength that you are measuring, the absolute station position relative between them, and the source position in the sky. But also, you really need to keep track of the times, of the arrival times of the signal to each station, because otherwise you cannot combine those ones. But of course, all these stations are in the Earth, and you have a vast number of different small movements that you need to incorporate when you are combining these ones. So this is basically a fundamental model that is considered at the correlator level, which is where you combine the data from these two stations. And then you do it for each pair of antennas in your array. So actually the correlator only does basically a geometrical model and accounts for that. you will receive the two signals from the two stations, and basically you are just correcting for that geometrical difference between those ones. And of course, here everything is relative to basically one of the stations, so you don't keep track of the absolute times, you just want the relative differences between one and the other. So from the signal that you receive from the telescopes, basically you stored the visibilities that are complex numbers per baseline, so antennas I and J, and you have the information about the phase and the amplitude there. As it is for per baseline based, you typically consider the baseline vectors, which is basically the difference in position between the two antennas, and you use a convenient system of reference, which is U, V, and W, which means well, it's set as W pointing to the direction of the source, and U is the axis between east and west, and V is the axis north, south. So that means that from the point of view of the source, you only play with two, or mostly you only play with two units, U and V, which is the UV plane that you've already seen in previous lectures. And this is basically how that baseline, so the separation between the two stars, is seen from the source. But of course, these complex numbers is basically the signal that you are recording from the sky. So at the end, what you want to measure, or what you are measuring, is the sky intensity and that particular field in the sky. And then you are doing basically a Fourier transform there, and this is what you are storing, the visibility is there. But of course, the signal that you are recording from the telescopes is not just the Fourier transform of the real intensity of the sky. So assuming that given a intensity function in the sky, you will expect some given visibilities per baseline. However, we have a lot of effects that comes into account and affects that data. So what we are actually recording, the observed visibilities, they are proportional to what you expect from the sky, but you have a lot of effects that alter that signal. So coming from the right to the left, of course, the signal that you are getting is affected by opacity and path length variations from the atmosphere. So that means that you have a perturbation in the real signal you will expect. Of course, you need to take into account also the paractic angle corrections, because you are tracking a source, typically during different hours. So you have an effect there that affects the phases that you are recording directly from the stations. And of course, the source during observations may change the elevations, which means that you also have some dependencies there, especially for different antennas that will have different elevations. Of course, you're recording in general two polarizations. Ideally, those are orthogonal, so you have a signal in the right channel and the left channels, and they are completely independent. In practice, that's never true. You always have some leakage from one to the other, from different telescopes. So you always have also some terms there that you need to correct for. And the main ones, as always, you have effects that alter the expected gain amplitudes and phases that you are recording in the telescopes. This is the main purpose that is corrected by band passes and fringe fitting. Then we have some instrumental effects, and as you saw during the plotting yesterday, you typically have a bandpass shape that is not completely flat for the bandwidth that you are recording, but you have a different response in the instrument for different frequencies within the band. And this is something instrumental that needs to be corrected to recover the true amplitudes in the signal. And of course, at the end, you may have some errors that may be dependent on the two antennas. So here I call them baseline-based errors. So this is true in general for any interferometer. then the particularities of VLBI is that you have antennas that are really far away from each other. So compared to connected interferometers, you typically have the stations in the same place, roughly. So that means that all the perturbations coming from the atmosphere are roughly the same for all your antennas. Also, the data streams from the two antennas goes directly to a correlator. So just knowing the path lights that they have the signal, you know at which times you need to combine or which delay you need to incorporate there. However, in VLBI, this is not true. The stations are really far apart, typically not connected or directly connected between them. And that means that you really need to keep track of the clock information, so the timestamps, the data that you're recording individually per station. And it's only once you arrive at the correlator level where you synchronize the two data streams to obtain the coherent combination of the data. Additionally to that, you may expect completely different atmospheric conditions from one antenna to the other because you are separated thousands and thousands of kilometers. And another effects that you may have is that stations have proper motions. They move because they are in different Earth tectonic plates in general. So that's why you really need to know the absolute position of the stations and also keep those ones up to date. So all these things introduce different, if we focus on phases, different delays in the data that you're receiving and some perturbations with respect to the only geometrical model that you are taking into account in the correlator level. So you correct for the first term, which is the geometrical delays, as we mentioned before. Of course, you may not know completely perfectly the position of the station, so you may always have some small variations there, or offsets. Of course, the phases for different baselines may be affected by the fact that maybe your source is not strictly point-like, and where in the center of your phase center where you are correlating. So that also may introduce some phase variations. And of course, the important parts and that they are time variable and you cannot predict is the propagation effects. So the signal goes through the atmosphere, and depending on your frequency, you may be more affected by the troposphere if you're observing at high frequencies, or the ionosphere if you're observing at lower frequencies, like below 5 gigahertz. And of course, always you need to take into account that you have different instruments, so they may already introduce different instrumental effects, delays in your signal paths. Plus, you always will have some signal. So all this means that if you observe a compact source, you will see an evolution of the phases, and you can see here the phases versus time for different baselines in one particular EVN observation. You will always see from the raw data that the phases evolve with time. You expect at least a smooth evolution, so you can correct for it. This is what you do in the data reduction. And you also can notice that this evolution may be different for different baselines, especially for different baseline lengths. So the difference in VLBI is that the evolution of these phases may be much faster than what you would expect in a really compact interferometer, a connected interferometer. So the only way to properly correct for that is if you don't correct directly the phase evolution, but what you fix is actually the derivatives of the phases. So you correct for the delays, which is the evolution of the phases versus frequency, and the rates, how they evolve with time. And this is what we call fringe fitting. And I'm not going to go into the details here because you will have a dedicated lecture after this one by Des about fringe fitting. So he will explain everything up to you. So one thing, as you can see here, is that you really need good signal to noise, of course, to be able to trace the evolution of the phases. That's why you always want to observe bright sources. Of course, your target in general will not be that bright, or it can be resolved. So you may not have such much signal there. And that's why in general, or for faint sources, you really need a second calibration source, likely really nearby to the target. So the corrections that you're applying, you assume that they are exactly the same ones that the target could require. Also, in the cases that you really want to recover the absolute astrometry, the absolute position of your target, you also need some calibrator sources, at least to compare with the absolute positions on those ones. And of course, as you can derive from the previous slides, you may have some effects that are just instrumental, purely instrumental, or other ones that are sky dependent, so position dependent, direction dependent, sorry, which are basically the ones related to the atmosphere conditions, so propagation effects. So in that case, you know that for different positions of the sky, the corrections will be different. And that's why if you use a phase calibrator, a calibrator source to correct for these effects, you really need it to be really close to the target. So ideally within a few degrees, the closer it will be, the more similar corrections it will need compared to the target. But of course, not always you have a really bright calibrator close to your target sources. So for at least to correct for those instrumental effects that do not depend on the direction that you are pointing to, you may prefer to observe what we call fringe finders of one-pass calibrators that may be farther away, but they are typically brighter because you pick a much brighter source. So that allows you to correct for everything that is not direction dependent with a much higher signal to noise. So the corrections likely will be better. And if you're interested in polarization, of course, you always need to observe some source that provides polarization information so you can correct for it. So a typical EVN observation or VLBI observations can look like this. You typically observe at least a couple of times a fringe finder that typically will be your strongest source, so it will have the highest amplitudes. That means that for phases or other conditions, it will provide to you the higher signal to noise. But this source is quite far from your target, so that means that the solutions that you may find for the phases cannot be directly applied to the target. On the other hand, if you're observing a faint target, means that the amplitudes will be kind of consistent with the noise that you expect for those baselines, and you will not be able to recover the phase information because basically your signal is dominated by noise, not by the source signal. So that's why you observe the phase calibrator in between, the opposite. You observe the phase calibrator and then the target in between. So at least you have a source to derive solutions, correct for the evolution of the phases, and then extrapolate those solutions to the target. So this is basically the general concepts that we will go during the data reaction. If we start with that, as you already observed yesterday, we have two first steps before going through the fringe fitting. One is the paractic angle corrections, that is also related with which kind of mount type your antennas have, because you're observing with different orientations the sky, so you need to correct for that. Otherwise, you will have a sinusoidal phase trend in your data. And the second one is the a priori gain calibration. So what's the real Jansky flux level of your amplitudes recorded by the station? In APES, all those two things were integrated in the data provided for the EVN, so you didn't need to care about those ones. In CASA, it's a bit different, just for the moment. So for the paractic angle, you always need to keep in mind that you need to set the parang flag equals true. So you are considering this effect. And then yesterday, Mark already mentioned how to apply the gain calibration from the thesis values that we provide with some external scripts for now in CASA. So let's focus on this gain calibration. Probably several of you are coming from connected interferometers like PLA, Westerbork, ATCA, where you typically observe an amplitude calibrator. during your observations. So this is typically a point-like source with a really stable emission. So you don't see any variability at all. So you know the absolute flux that this source should exhibit. So as you observe it in your observation, you just need to scale out the amplitudes that you're observing in your data to the correct or the expected amplitude for this source. And you apply the same correlation, the same correction for the other ones. So that's easy. That already gives you the absolute flux that you would expect, and it corrects all the amplitudes in all your sources. However, this is not possible in VLBI, mainly because two reasons. One is that most of the sources on VLBI scales, they are resolved to some extent. So that means that the sources are not longer point-like sources, so you will not expect the same amplitude for all baselines. So in that case, either you have a really detailed model of your source at any given UV distance or orientation, or you cannot just scale up or down your amplitudes. And the other thing is that if you find a source that is completely compact, even on VLBI scales to millisecond level, then that source is likely to be highly variable, because mostly they will be Blazer if it's a strong one and extragalactic, and that means that it will likely show a high variability. So that means that you don't have an absolute amplitude, or you don't know the absolute flux to scale them out. So that's why you cannot use an amplitude calibrator in VLBI data, but you need to rely on the system temperatures that you measure during the observation. So again, this is radio antennas. Basically, typically you measure the powers in units of temperature. So it's what it will be equivalent from a black body emission. And basically the system temperatures are the power that you are measuring, assuming that you don't have any contribution from any source in the sky. So just the noise of the antenna. So of course, given these powers, you can always, or your purpose is to set a relation and conversion between power units, temperature units, and flux, real flux in the sky. So for that, you really need to know what's the sensitivity or the absolute gain of your antenna, which typically is called the dPFU, the degrees per flux unit. So how much temperature you have, or it's converted to a flux unit. And basically what you do during the observation is incorporating or triggering an artificial signal and also setting it off. So by measuring the relative intensities that you are measuring at the station, you can set or get an estimation of these conversions. So that's why you measure the system temperatures during the observation, and then you also have the gain curve, because of course the sensitivity of your antenna will depend on mainly the elevation that you're observing to. Lower elevations will have less sensitivity. So typically you disentangle those two values, you get an absolute gain for the antenna, and then you have a gain curve where you apply depending on the elevation of the source at each time. One important thing here is that this is just an estimation, or your conversion between temperatures and power and flux, sorry. Precision in the measure fluxes, in the final measure fluxes from your sources. Okay. So before going to just the rest of the calibration steps, I will make a reminder for some of you, and it's about Fourier transform. This is always nice and recommend to keep in mind, because to understand what is coming now. So most of you, if you remember a delta function, if you do the transform of that one, it's always a constant. That means in the 2D plane, let's say that the delta function is what you will expect from a really point-like source, is that you will expect the same amplitudes at any given UV point. So that means that for all your baselines, that will be different UV points, different UV distances, you will always have the same amplitude. But this is only true if the source is completely unresolved. If you have a resolved source that can be here characterized as a Gaussian, for example, you know that for different UV distances, the flux will decay, also kind of a Gaussian-like. So for the short baselines, you may expect a really high flux, but then that flux will decay for longer baselines, even going to zero if the source is completely resolved. Okay, so keep always in mind to understand everything the calibration that a point like source will have the same amplitudes for all baselines. But of course, if it's resolved, you will expect to see lower amplitudes and then less reconstruct phases on the longest baselines because you will have less signal to noise. So why I'm saying this? Because to explain all the phase corrections or all the data reduction steps that you typically conduct, I'm going to use a diagram where you basically see the amplitudes and the phases and how they evolve with frequency and time. Okay. So of course, the basic calibration always assumes that you have a point like source, and that means constant amplitudes, baselines, and you set relative phases. So at the end, you just set them to zero. And that should be always true at any given time during your observation and also at each frequency, the ones that you're observing. So, sorry. Now we will focus on the data calibration steps. Based on this is what you will expect for a strong source and a particular baseline. So both versus frequency and time, the amplitude should always be constant to a level, which is the flux of the source. And then you will always expect phases around zero. Okay, you will always have some noise there, but around zero always. So in reality, if you plot the raw data from any VLBI observation, what you see is something like this. Okay, so the amplitudes are not flat, but you see the bandpass shapes. So meaning that you can distinguish the different subbands where your data were divided, and you see that the signal goes basically to zero at the edges of those subbands. In some particular cases, you may have a slightly different amplitude dependent with the time. And in the phases, they are never flat. As you saw in the previous plots, you always have some trends, especially by time. And then in frequency, you typically have a slope, but also some jumps between subbands. Okay. And this is, of course, for a bright source where you can reconstruct quite well what's the amplitude and phases. If you observe a faint source, what happens always is that you're dominated by noise. So basically, you cannot say anything about amplitudes. They are consistent with just the noise or zero. And the phases will be completely random because what you are recording is dominated by noise, not by actual signal from the source. So going back to the previous plot, this is why you always use a calibrator source if your studies are faint to calibrate the data. Then this one summarizes basically every step that you need to do in data reduction. So we will go one by one and see all the different steps that you do. So let's start with the phases versus frequency. This is not a step that is strictly necessary in all cases. We recommend in most of them, and you will see why in basically 3 slides in the future. But basically here I mentioned that you have a slope in the phases and then some jumps between subbands. And those jumps are basically related with the instrumental effects that you have in your station. Some of the subbands may be recorded through a different hardware within the station. So that means that actually the path length is not exactly the same because different hardware may introduce a few small delays in the signal. And this is what you're seeing here. The instrumental delays just originated by where within the antenna the data went through. So this means that these jumps are strictly instrumental, they are not affected by where in the sky you are pointing to, and should be completely constant in time, should be the same. And that means that you don't need to care about the time dependence on these ones, and you only want a strong source, the strongest one, because then you can have a much better signal to noise and you can fix for them and correct for them. And this is what we call the instrumental delay correction. So again, these effects are not time dependent. So you only need to consider a small amount of data, enough to have a high signal to noise, but not long enough that you may have some other time effects that may alter the solutions. So we typically, you consider a couple of minutes, for example, in your fringe finder because it's the strongest signal, and you get a solution for those ones. And the goal is to correct just those jumps. And of course, you don't want to correct for any time dependence that your data may have here, the raw data. So you set 0 rates, so you're not correcting for the rates, so the evolution of the phases versus time. So once you apply the instrumental delay, at that particular time, you will flat the phases and then you correct for these jumps. But if you look at the data at different time stamps, you will still see a slope in the phases that will be different for different times, because you are not correcting about the evolution of the phases. Here, you are only correcting about those jumps that you saw at the beginning. So the important part is that now all the phases are completely continuous across your band. So if we move to the amplitudes versus frequency, you are quite probably familiar already with the bandpass shapes here, that this is an artificial shape that you introduce to split the band that you're recording, or where your telescope is not sensitive. And then this is an easy correction. This is the called bandpass calibration. You only want a strong source. Again, it's just an instrumental effect, doesn't depend with time. So you may only want to correct, get one correction for one of the sources in your observation, and then apply the same correction for the whole observation, because these shapes will be the same for all the sources and for all the times. So with the bandpass correction, as you may have seen in the plots yesterday, you will end up with flat amplitudes across your band. This is the ideal case. In a few particular cases, you may still see a small deviation from that one. So you may have flat amplitudes, but slightly different across your different subbands. Of course, this will only then be corrected by self-calibration once you have a better model of the sources, but these are typically small enough that they are not that relevant. And in the same way, if you do the amplitudes versus time, you may have in some particular cases, especially when you're observing sources with low elevations, that the amplitudes may be dropping slightly from what you would expect. And this is basically because, again, at the lower elevations, you may have less sensitivity, and maybe the a priori gain calibration did not took everything into account there. But basically, you can only correct for this during self-calibration. So once you have a full model of your source and you know the expected amplitudes. But then, sorry, we go to the main calibration step, which is the fringe fitting. And in this step, this is the only thing that is left up to now, is the phases, the evolution of the phases along the time, and also along the frequencies. And this is basically one of the most important parts that you have in the data reduction. So you see from the raw data that the phases will evolve quicker or slower across the time. And of course, if you remember, you will still have some slopes across your band. So the purpose here is that make all the phases flat. You really need to correct for all these propagation effect that you had here and correct for the artificial evolution of the phases. This is what fringe fitting does. So it corrects for the delays and rates at once, doing just less square fitting. So you are correcting for the evolution of those phases. And again, these are direction dependent. So you either solve them directly in the target if they are is bright enough, or you only can correct for them in a source that is nearby. So the phase calibrators needs to be just within a few degrees, so the perturbations are roughly the same for both sources. And here, you can do two things. The standard one, or one of the ways, is to produce, of course, a solution for a given solution interval that must be proportional to how fast the phases scale. So it allows you to have enough signal to noise, but also not don't taking into account the fast variability that you see. And in terms of the frequencies, you may combine your whole bandwidth. So in that case, you are increasing the signal to noise. But in this case, of course, you need to guarantee that all the phases were continuous previously. So that was the motivation of the initial instrumental delay correction. On the other hand, you can just provide a solution per subband. So in that case, the instrumental delay is not necessary because in the global frame, you will correct for those jumps that you saw in the phases across the different subbands. However, if you get a solution per subband, means that you are getting a lower signal to noise because you're not combining the whole band. So that's why, depending on how bright your calibrator is, you may prefer to conduct the instrumental delay correction and then a global fringe, or if you have enough signal to noise, you can do a global fringe and that's it. But in that case, you need to do it subband independent. And of course, all these corrections have been done in the calibrator. What you are interested is in your target, that again, in most of the cases may be faint enough. So that's why you observe the calibrator and then the target in between, because you will get solutions, amplitude and phases for your calibrator, and then once you characterize the evolution of the phases and you correct for them, you will apply those corrections for the target. At those times, you were dominated by noise, you don't see a trend in the phases, but then you hope, it's almost always the case, the corrections that you apply in the calibrator right before and between, it will be continuous, so the same corrections applies to the target. So that's the path to...
5 minutes, Benito.
Yeah, thanks. So that's the path to move from the raw data and calibrated information that you have, looks like the blue lines, to a fully calibrated data set, as the green one. So, of course, once you're done with the data reaction, you're interested only in the targets, you don't care about the calibrators. You need to apply the solutions to and transfer them to the target source. And then you focus on the imaging. So you image your source, and then in some cases, if you are lucky enough, especially for calibrators, you may self-calibrate to improve this calibration. I will not focus now in details in any of those ones because you have a dedicated lecture on imaging, and then you also have a dedicated lecture on self-calibration. But before ending, I would like to do 2 remarks in the 2 steps. One is imaging, and basically important differences with respect to connected interferometers. Because if you come from analyzing VLA data, for example, or any connected interferometer, there are a few small details that you need to keep in mind when analyzing VLBI data. First, the UE plane is less full than in connected interferometers, or typically it is. So that means that you have larger gaps. So it's poorer covered in this kind of observations. And that means that the noise that you will expect in the images deviate from the typical Gaussian behavior. So you don't have a Gaussian noise, and that means that actually across your field, you will likely have strongest spikes as you expect from a Gaussian distribution. And that means that if you don't know the a priori position of your target, you typically need to set a level of high sigma, typically, to claim a detection, because across your field, you may have spikes that look at a 5, almost 6 sigma level, and they are not real. The other one is that also related to how you reconstruct the UV plane, but also the amplitude measurements there, is like you need to measure flux densities a bit more carefully than in connected interferometers. And also you always have different ways to measure flux densities. So traditional one is through the image plane. You have already an image, so you measure fluxes there, either with boxes, fitting Gaussians, and that's in the image plane. So you are not taking out the contraction of your synthesized beam or how a point light source would look into your sky map. And that means that the fluxes that you get there may be slightly different or have subtle difference than if you measure the fluxes just by fitting your UV data. That's also possible and sometimes can provide to you a bit more reliable fluxes. And of course, given that this is an interferometer, you are not obtaining a UV point across the whole UV point, across the plane. You are missing several spatial scales. So that means that you only have some different scale information. And that provides that if you have large gaps in your, for example, UV distance, they may be different source shapes that provides exactly the same information that you are seeing. For example, in this case, if you have only short baselines or really long ones, but you are missing the information in between, you will have exactly the same response for a completely point-like source or a ring source, okay? So you need always to keep in mind that depending on which gaps you have in your UV plane, you may be missing some special structures. And the last one is about self-calibration. You'll have a lecture dedicated to that, so you will have more feedback there. But always keep in mind that self-calibration may basically modifies your actual data to fit your model, your source model. So that means that if your model is not completely accurate, you will introduce some artificial deviations in your data. Okay, so that's why you always need to be careful and be confident in what you are doing there, because it's easily, especially in amplitude, to scale up and down artificially what you're observing. And then in your target, you will end up with completely wrong amplitudes or even shapes. So just to finish, you have a summary and also from other lectures about all the steps. And as you saw here, it's always also relevant to how you conduct observations on which kind of sources you are observing. So the first step to produce a better data reduction is always to have a good scheduling that fits the purpose that you want to achieve in your observation. So don't forget that scheduling is also an important part, and you also have some feedback about what you should schedule and what properties those calibrator sources should achieve to be able to obtain a good data reduction. So that's it. Thanks.
Thanks, Benito. Thanks for the very nice talk. It seems like some people have lost some audio, so as Ilse has put in the chat, please go to the YouTube stream, which seems to be okay. Anyway, we were okay, but it seems some people were losing it. So I'll pass over to Mark, who should be able to summarize some of the questions we've been having through Mattermost and the Q&A. So Mark, whenever you're ready, you can grill Benito.
So the first question nicely ties into the last comment that Benito made. So the question is, during VLBI observations, how long are the target scans supposed to be? Is there a rule of thumb to reobserve, well, the question says FaceCal, but reobserve a calibrator, I suppose, after a particular amount of time.
Yeah, it's a good question, actually. So, of course, you cannot always provide an absolute value that is the one that you should observe. The thing is that you want, as long as possible, your scans on the target, because that will mean that you are getting more data, of course, in your target. But on the other hand, you still want to recover the solutions if you are doing phase referencing from your phase calibrator, for example. And then you need to keep in mind that you really need to have a good extrapolation of the solution from the calibrator to the target. So basically, the limitation is how the phases evolve with time. So the solutions that you obtain for the calibrators will nicely interpolate the ones for the target. That, of course, depends on elevations and baselines, but for a typical VLBI observation, the only factor that you may keep in mind at the beginning is just the frequency that you're observing. The higher frequencies, the faster the atmosphere effects evolve. So as reference, let's say that at 5 gigahertz, we typically set cycles of around 5 minutes, meaning that you may spend like 3 minutes and a half on your target and then 1 minute and a half on your calibrator. Okay, in the calibrator, you only need as much time as provides to you a good signal to noise. So it depends basically on how bright is that calibrator. Typically between 1 to 2 minutes is enough for a bright source. And then around 3-4 minutes on the target. So a full cycle of 5 minutes. If you go to lower frequencies, 1 gigahertz or so, you may go longer. So on the scale of 6-7 minutes, for example, for the whole cycle. And if you go up to 20 gigahertz, so higher frequencies, you may need to spend basically 1 minute target, 1 minute calibrator, because otherwise you will not get good solutions for the target. So we are talking about basically those levels there. Yeah, of course, if you want better solutions for astrometry on everything and you really want the best possible solutions and you don't care that much about the signal to noise on your target, you may reduce the cycles, or the opposite. If you don't care that much about how the solutions, because the target will be bright enough to self-calibrate later, then you maybe go a bit longer. But let's say at 5 gigahertz is always recommended of the order of a 5 minute cycle. So considering phase calibrator and target time.
Thank you, Benito. Then we have a question on Mattermost. How important is it to have the fringe calibrator at the start of the observation and at the end of the observation?
It's not necessarily. The thing, for example, for the AVN, we always recommend to have at least 2 different scans on the fringe finders. This is in principle not needed. With one, you have enough, and then you don't care where you place it. The problem is that during an observation, and depending on how long it lasts, but let's say a standard on average 8-hour observation, you may have stations that drop or they couldn't observe that source, or you have other effects, so you miss the data in those scans. So for the fringe finder, you really want to have information from all the stations. So that's why if you always schedule 2 scans, as far apart as possible, kind of you have good chances of getting all data from all the stations when you were working properly. So this is just basically to avoid missing information from one station at the scan where the fringe finder was observed. So sometimes we schedule just at the beginning and at the end, because then the chances that if something happened at the beginning of the observation, at the end, everything was solved and everything was working, or the opposite. But it's not strictly necessary to schedule right at the beginning or right at the end. And of course, depending on the sources that you're serving, you may prefer to have it right in the middle and then another any time. The only, I will say that, yeah, the only issue is if you want to reconstruct like geoblocks or polarization calibrations, reconstruct the correct for the D terms or so, where you really need to have different scans on the fringe finder or polarization calibration. So in that case, you really need different times and basically covering the whole observation. But for fringe finder purposes, doesn't matter where you schedule them. And we recommend at least 2 scans if the observation is long, just to avoid possible missing data from a telescope.
Okay. Next question is, why did you leave out the K matrix from the delay term in the measurement equation you showed?
Oh. Okay, for no reason at all.
Well, I think I know the answer of that. What you copied the what's in the CASA manual for that.
Yeah, exactly. I took basically the reference that CASA was using.
So basically, that isn't specifically targeted to VLBI, and of course, some of the delay is actually in the tropospheric delay that you're correct.
Yes. Yeah. So basically, that's the standard form that CASA is written. But yeah, didn't focus also in the details there. But in general, yeah, the delays that you have, you can fit them in the other terms inside. Depends on how you account for them at the end.
So we have a couple of more questions in the Q&A. So why do we see those up to 6 sigma spikes in the image field? Can you explain that again?
Yes. So let's start with the more natural one that comes typically when you have a connected interferometer with a lot of antennas, let's say the VLA, okay? In that case, you are observing a field, you do the image, and there typically the noise is just Gaussian, okay? So it follows a Gaussian distribution. And in that case, you know that, okay, 3 sigma spike will have 99.99% probability. But that assumes that your noise is Gaussian. And this is only true when you are recovering or feeling the UV plane kind of accurately. VLBI observations, you may have a lower number of antennas, but maybe even you have a larger number of antennas, but they are more spread away. So the empty gaps in the UV plane are much larger. So in a typical EVN observation, you may even have a hole between the short and the long baselines sometimes. And that means that when you are reconstructing the image, the sky image, that noise is not Gaussian anymore. Basically the tails on the lower and the high levels are higher than expected from a Gaussian distribution. So that means that you have a higher probability of getting, just by noise, stronger spikes than what you would expect from the Gaussian distribution. So basically, at the end, that's the only reason. In a field, let's say when you do your field of 1 arc-second or any given field, then you have a higher probability of having stronger spikes there. So basically the 6 sigma cutoff, as I mentioned there, for any random position in your field is kind of equivalent to a 3 sigma probability for a Gaussian distribution. So anything above 6 sigma there in the field, you can be sure that it's likely to be a real signal from my source and not just noise. But basically it's just because with the purely field UV plane, you have a higher probability of having stronger spikes than if you compare with a Gaussian distribution.
Thank you. And then
We'll
the
make
last
this
one.
the last question. Sorry, Mark. That's okay.
Yep. The last. There's still one question more, so I think we still have a minute for that, because I think it is a short question. Could you mention something about the choice of the reference antenna?
Oh yeah, that's a good one actually. Yes, so in data reduction, you always set relative differences for everything. So you always keep one antenna as reference, and then you just correct everything else relative to that one, or all the baselines to that antenna. So for that, you really need to know that that antenna is behaving as good as possible and likely observing all the time. So at least in that case, what you want is typically the antenna that provides to you the best signal to noise, because that means that for all the baselines, you will also get the highest signal to noise. And then an antenna that didn't have any problem or observed during the whole observation. Okay, so in the case of the ABN, most of the times it's simple. FSBR is typically the most sensitive antenna that you have, is quite reliable. So it's the one that you typically use as reference antenna by default. That's in an homogeneous array where you have an antenna that is significantly more sensitive than the others. Of course, if this antenna didn't observe for most of your observation, you may prefer another one. Also in CASA, you may have solutions for that reference antenna, and if that one is not available, it will change to another one. But then it's a bit trickier because you really need to be careful, especially for astrometry purposes, if you really need a really good astrometry, because the changes between one reference and the other may introduce some offsets at those particular times. So the general rule is like pick always the one that observed during the whole observation and is the most sensitive one. So for that one, you will get the best solutions possible for your observation. And yeah, I think that's kind of the summary there. If you want more details about those ones, just do follow-up questions here or in Mattermost.
Okay, so Mark, if you could put the last question into the Mattermost channel, then Benito, you can answer this in your own time. Thanks again, Benito, for the nice talk, and thanks for the help, Mark, with the questions. And you've got some nice congratulations in the chat as well for you, Benito.
Thanks.
So next up, we've got Des. And Des is going to talk about the latest VLBI tasks in CASA. So whenever you are ready, Des, then please take it away. I'll give you a 5-minute warning if that's okay. And yeah, start whenever you're ready.
Okay. Am I audible now?
Yes, you are.
Okay. So Benito's given us a wonderful talk on the calibration practicalities of VLBI in general. And Mark's already given us a wonderful talk on the calibration infrastructure in CASA. And so I'm really going to be hopefully complementing those talks with a few details on some of the specifics of the CASA-VLBI tasks that I've been involved in implementing. And I hope that the interference between our talks is constructive. Yeah, another title slide. Okay. So in practice, once you've handled the VLBI specific way of dealing with gain and amplitude calibration and system temperature, the only thing that was really missing from CASA to do VLBI was fringe fitting, and Benito's discussed a fair bit about fringe fitting. I'm going to really only talk about fringe fitting. I'm going to look at VLBI from the point of view of fringe fitting, why it's necessary, and how you do it, as well as a little bit of history. So CASA was developed by NRAO starting in the 1990s. For a long time, it's been used for the VLA, and it's also been adopted by ALMA. And there was always a plan that it would be a generic package that would be able to do interferometric radio interferometric data reduction for any array, more or less. But the implementation for a long time didn't have a fitting task, and that's essentially the only thing that was really missing. And so that's what I talk about. So Jive got involved in this because the Black Hole CAM project offered funding for us to work on CASA and make it finally VLBI ready. And of course, as you've probably seen, that it was successfully used. Michael Janssen is going to talk, I think, about his work developing a pipeline that was used as part of the EHT project to image the black hole that we all saw in the newspapers around the world. And as a result of that, what came out of that is that you can now do VLBI in CASA, which is why we're all here. Now, an interlude, which I've attributed to Bracewell, but I don't think he said it, but I just thought it would be convenient to have somebody eminent to attribute it to. Now, the thing is, when you're looking at phase, a complex exponential of phase that's a function of anything at all, then locally it's going to look like a Fourier transform pair of coordinates. So you can take the derivative of your function of something, and then introduce a new coordinate which is that derivative, and then you automatically have a Fourier transform pair. And we're going to see how that becomes a thing when we do the when we develop the theory of fringe fitting. So again, this is something that Benito showed, but it bears repeating. I think that when you're doing interferometry, you're trying to measure the coherence of an electromagnetic field, and to do that, you want to synchronize your observations. So a very important part of that is you calculate a geometric delay that you add to the various antennas so that your observations are then of the same wavefront. And that's how you make sure that your coherence measurements are meaningful. Then you downmix those observations, and you add the geometric delay before you correlate, and that's your end product. So what you're really doing is looking at the projected baseline at equal times and turning that into some measurement of the sky. And anytime you get the delay wrong, if your geometric delay isn't correct, then that degrades your quality. It means that your phases are not aligned, and then you need to correct for that. Now, and in VLBI, it gets, of course, much worse, because here I've drawn a picture of the Earth, which is rotating, and you've got your two antennas now are in different places on the Earth, and you're still trying to do the same thing. And we have a program called Calc that tries to do this, and it bears in mind ocean loading and plate tectonics and atmospheres as best as it can. But fundamentally, you're using now different clocks at different stations, and you're using different local oscillators, so your frequency standard is different. And that means there's a residual degree of uncertainty that you don't know a priori when you're calibrating the data. And that's what fringe fitting is designed to deal with. So so when you have a delay, it corresponds to a slope in your phase against frequency, right? Because the higher the frequency for a given delay, the further the phase front advances. So there's actually some physics behind that. And when you have, if there is a specific delay, you should be able to pick it out quite cleanly, you would hope. So here's an example of the VLBI procedure of fringe fitting, right? I'm not talking yet about how it works. I'm just simply showing what you're doing, as Benito did. And you see that before you do anything, you have every different color in this plot is a different baseline, and you see there are slopes of various kinds, and these are the different subbands or spectral windows in CASA talk. So they're not aligned, and they're sloping because of the residual slopes from instrumental effects. And this manual phase cal, as we call it, in VLBI procedures, there are actually use phase cal tones to try and line up the different spectral windows. But here we're doing it by simply looking at a bright calibrated source and saying that if we have enough signal to noise that we can fringe fit all our delays and rate, and no, just the delays actually. If you take the delays out of all of these things and make sure that the phases across each spectral window are reduced to 0, then you know that in any other scan that you look at, the phase across the bands will be aligned. So we'll see an example of that here. Once this is after you've applied the manual phase color, and you can see that every different color on a different scan, we're looking at a different scan, so there are residual delays, but they're now all completely aligned across the different bands. So that means that we can now do a multi-band fringe fit and get higher signal to noise, and our life is good. And once we've done that, we correct that, and now our phase is flat. And this is as if we're looking at if we're looking at a compact source, which we will be when we're trying to do the fringe fit. And this is our calibrator source, so you want it to be a nice compact source that looks quite a lot like a point source. And once you've done that, you have a nice flat phase, and then you know you'll be okay to apply that to your target source, and then you'll be able to do imaging and your life will be good. So one thing about manual phase cal is, of course, that you're going to apply, you do your manual phase cal on one short section of a very bright source, your brightest source. And then when you do it, you write down a 0 rate term, right? Because you don't, when you're going to apply it, you apply it to the whole data set, and you really want to take out the delays. You don't want to be extrapolating the rate term, otherwise it will completely ruin your data. So you'll see in the tutorial, and all of the practicalities of this are covered in the tutorial for VLBI with CASA. You'll see that that's a very important detail. And this is something that when you do the multi-band delay and you want to apply it in CASA, this is a CASA specific detail. You'll see that you make a new multi-band delay table. You can choose what file name you like for that, and I always like to call it MBD for multi-band delay. So you add a new one, and you have chosen your appropriate solution interval, and you've told it that you want to combine the spectral windows here. And you, in this case, I've said I want to do it for the whole of this field, because that all effectively amounts, that's my phase calibrator source. So I want to do the whole thing in one go. And because I'm using really good data, test data, I can afford to say that I'm not interested in anything with a signal to noise ratio of less than 50. In practice, you're going to have much smaller numbers than that if you're doing, real astronomy. This is my single band delay, my manual phase cal delay that I've had to apply, and these are the two a priori calibrations that we've imported. But what the point is that when you apply this calibration, you have this SPW map thing, and you don't want to say anything about how the amplitude calibrations and the manual phase cal, those are all fine. So you kind of give those empty lists in Python. And then here, this is the interesting term, because you take your multi-band delay in CASA's bookkeeping is given a spectral window number, and that can only have one spectral window number, and it will use the lowest spectral window in the set. So if you do it for all the bands, that will be probably 0. And so you say, I want each of my 8 bands should get you use the spectral window 0 data from the multi-band delay, and it looks like this. And the point is, you can do other things with this syntax. This is by adjusting this syntax, it will allow you, if you're cunning enough, to apply continuum calibration to a spectral line observation. So I put that in because Mark promised I would, and I thought I might be better off if I kept his promise for you. So again, it was asked yesterday, what happens if you have you have more than one band, but they're widely separated in frequency space? Can you still do a multi-band delay? And of course, well, not of course, but as it happens, the answer is yes. Whenever you do the multi-band delay, we'll take a frequency grid that goes from the lowest frequency you have to the highest frequency and is uniform across that frequency space. Now that means if you have widely separated bands at the moment, then you will be, you're going to do we'll come to it later, but you're going to do a Fourier transform across that space. You put all the data onto one frequency grid and then take the Fourier transform of that. And that will be quite an expensive process when you're Fourier transforming a lot of zeros, but it does work, and it doesn't cause a lot of big problems. And the same is true of ALMA, where the frequency grids are not completely uniform between bands. So, in practice, when I make a uniform frequency grid, I'm moving the data from a frequency to a very nearby frequency, and I use only nearest neighbor interpolation, and that could be improved, and we're working on a method to improve that. But it does all work in practice. So here is another thing Benito told you about, that when you're observing in VLBI, you often want to use a phase calibrator near your target source. Your target source is not strong enough to fringe fit on directly, or also it might be non-compact, so it would be unpleasant to work with in fringe fitting. So you pick a nice strong calibrator near it, and then you alternate the scans. And as Benito said, you want to alternate fast enough that you're inside the coherence time of the atmosphere, which is frequency dependent. And then, you're going to be linearly interpolating the solutions from the phase calibrator on either side. So it's very important that that's a meaningful operation. And whether it preserves absolute spectrometry, now Benito suggested it did. And if you know exactly where your calibrator source is, and it's close enough that your atmosphere can be meaningfully treated as exactly the same as your target source, then you're good. And if any of those things become less true, then you're starting to work in compromises. So the details of this phase transfer, how you exactly the syntax and how you do that in CASA, that's all shown in detail in the tutorial that you'll be working through. So I haven't put up a lot of the Python syntax here. And there's one other piece of, folklore or general practice that we've seen the bandwidth. The band pass for each band has this characteristic slope where it's very strong in the middle and quite weak at the end. And you do bandpass calibration to bring all that to a uniform level. But when at the very edges of your frequency band, the amplitude is very low, and you might reasonably wonder if you can actually trust the phase at all. So there is a tradition and a long established practice that you should flag 2 or 3 points at the outside edge of each frequency, of each spectral window before you fringe fit, so that you don't get, your fringe fitter doesn't get misled or upset by any of the bad data at the edges. And there was a question in the previous talk, how should you pick a reference antenna when you're fringe fitting? And the answer Benito gave is also the one I'll give, that whenever possible, you use the biggest antenna because you'll get the most signal to noise ratio there. And that's Effelsberg if you're using the EVN, it's ALMA if you've got an instrument like the HT. If you don't have that, then you pick one that's geographically central, and of course one that's present in as many scans as possible. And then one last thing is that you really always need, when you're fringe fitting, unless if you have enormous confidence in your pipeline, then that's fair enough. But if you are uncertain in any way, you should always plot the calibrated data, right? Because let's go right back to here. This is what happened. This on the left is your data before you do any fringe fitting, and this is the data after your fringe fitting. It's really easy to look at it and say, this is now nice and flat. The phases are flat across frequency, and they're at 0. And you either you average across the whole time, or you look at subsections of your data in time, and you check that this really happened. Because if it did happen, then you're safe to go on to imaging. But if you don't check and it isn't flat, then you'll be producing complete nonsense, and your life will be bad. And it's very easy to look and see. So I strongly recommend that you always go and inspect your data after you've fringe fitted to at least some level to make sure that things are what you wanted them to be like. So, okay, now, Mark has told you in some detail about the measurement equation. It's a completely generic framework for discussing calibration of radio interferometric data, and it's at the heart of CASA's algorithms. Everything in CASA is done along the lines of the measurement equation, and all calibration effects are implemented as by two complex matrices called Jones matrices. But as a user, when you're doing fringe fitting, you tend to be thinking about delays and delays and delay rates. And of course, those are internally translated into Jones matrices and back out again as appropriate. So when you are plotting your the calibration parameters that you found, it'll be plotted, you'll be able to see the delays in terms of nanoseconds or picoseconds. And internally it'll all be translated back into Jones matrices, but you don't really need to worry about that. I mean, that's beautiful and true and of fundamental importance to the software and to the mathematics of the procedures, but it doesn't really matter to you very much. Now, when I started working on the fringe fitter for CASA, there was already the established model of APES, and of course APES has been the VLBI data reduction package, the industry standard for many years. And the APES, well, for many people, okay, there's also HOPS, and there are people who use HOPS, but in the EVN world, APES has always been the dominant package, and the fringe fitting, the way APES does it, was the industry standard that we wanted to come as close to as possible. So it was an explicit design goal for the CASA fringe fitter to be as like the APES version as possible, to have, wherever possible, to have the same options, to have the same results, and to, this was a necessary step to gain the confidence of the radio astronomy community, the VLBI community. So I went back to the original paper by Schwab and Cotton, and Bill Cotton was actually the implementer of the task in APES, and he wrote also the corresponding paper on how you do it. So I went back to that and looked at exactly what they do. And there's two stages when you do fringe fitting, two possible stages. First, you do a baseline based fit with a Fourier transform method, which we're going to talk about first. And that's where your reference station is most important, because you do all of your baselines to the reference station to get an initial estimate for your delays and rates from the fringe fitter. And the better they are, and then you cut off, you have a signal to noise cutoff at the Fourier transform stage, and only baselines that are higher than that will be included in the global optimization that comes next. So the better it is, the better your life is. And so here we are. We've got the true phase and the measured phase. We don't know the true phase, we do know the measured phase. And this is like a tiny fraction of the measurement equation, where instead of, for just one hand of correlation, we do the two correlation hands completely independently in fringe fitting at the moment. There are possibilities that we may adjust that later, but at the moment the two correlation hands are treated completely independently, and we have a observed phase at each baseline, at each time, and at each frequency. You can see we've got, and we assume that we're fitting a model essentially that a first order Taylor series expansion around some time and frequency for some small time and frequency window will be we can fit that to the data. And as we discussed before, that means that you can think of this as a Fourier transform. So if you take the Fourier transform of your visibility data, you can read off the peak delay, where in the delay and fringe rate space you have a peak, and that's your best fit for a model for those parameters. And when you apply those parameters, you'll get the phases flat, and then you'll be calibrated as best you can, or you'll be ready to improve that calibration at the next step. So here you are. This is a Fourier. This is the basis for the Fourier space, and then when I started doing this is industry standard, and it had been used before APES. This wasn't introduced with APES. But when I started implementing it, I looked at this and I thought, well, this is very beautiful, but I wanted to see it for myself, right? So I took some, when I was originally working on this in a Python prototype, I took some data and I did the 2D Fourier transform, and I plotted it to see if this was really, what it really looked like when you plotted the Fourier transform of the data. Do you actually see the delay and rate peaks the way you'd expected? And this is raw data on the left, and you really do see what you expect to see. It's you know, a sharp, there's some noise, and then there's a sharp peak, and of course the relative heights of the peak and the noise tell you your SNR ratio. And in practice, you would like to have, you know, a finer grained resolution when you do this Fourier transform approach. So in fact, what you do is you pad the data with zeros, and that means you, in Fourier space, that corresponds to smoothing it, and then you get this nice, beautiful, smooth surface, which is your, which you can read off the delay and rate off, and then on each baseline, you then have an estimate for your delay and rate. And then again, the Schwab and Cawthon method says that's fine, but at the moment we've only used data from each station to the reference station. So there's a lot of baselines that we haven't made any use of at all. And you see in this expression, there might be derivatives of the actual source phase that interfere with your estimates. So you know, you might be contaminated by some baseline dependent effects that are not geometric, that are not corrections to your geometric delay. They've come from somewhere else, and you can reduce that and make your life better if you fit a model of delay and rate. It's the same linear delay and rate model, but now you say you're going to do it on each antenna. Each antenna has its own delay and rate, and then you fit that to all of the baselines, and you do a global minimization where you also use the weights for the weights that you've established by the amplitude calibration you've used to weight the data in your solver, and then you throw that into a big standard least squares minimizers, and then you have an improved estimate. The way you've used ideally you've used every baseline's information, and you've weighted it accordingly to your estimates of how good it is. So that method was introduced by Schwab and Cawthon. It was implemented in APES, with 1 or 2 implementation detail adjustments. That's also what we use in CASA, right? And when we were developing this, we went to quite a lot of trouble to compare our results from the CASA implementation with the APES implementation. We checked that it was producing similar results in all cases. And that's it. So once you've done that, once you've found those parameters, that's your fringe fitting calibration, and you can apply it to your heart's content. Now, in doing that, for your phase calibrator, you generally you know, you take your phase calibrator to be compact. You want it to be like a point source as far as possible. But as Benisa said, in VLBI, not everything, even compact sources are not as compact as you might hope. So things look like a point source, but not completely like a point source. And you can address that with source models now. There's going to be a lecture on self-calibration and another lecture on imaging, so I'm not going to go into much detail. All I really want to say is that, first of all, fringe fitting on your phase calibrator, if you don't use a source model of your own, then you're implicitly using a point source as a model and fitting the best point source you can to it, and that's usually fine. That will work. That will be good enough for most purposes. Now, I don't know your purposes. Maybe it's not good enough for you, but for many purposes, it's good enough to assume that your phase calibrator can be fringe fitted as a point source. And if you want to, you can do self-calibration. And CASA, the main point I want to make here is that CASA does support source models. It has its own way of doing it. And if you have a source model, you can import it into CASA, and the fringe fitter can seamlessly make use of it and give you better results than you would do without it. Now, if you have source models that you've produced from APES as fits images, it's not currently completely trivial to import them into CASA. And as far as I know, I'm the only person who really knows how to do that. But if you really want to do that, I'm quite happy to tell you and work with you how to do that. NRAO have expressed an interest in making this a supported functionality, and I've given them all the information on how to do that, and we're waiting, for them to have the resources to implement and support that. But it's all possible. It can all be done. And here are some remarks about the implementation. Okay, so some people have asked, can we combine the polarizations, because the atmospheric effects of delay. If it's just an atmospheric delay, then it may well be that it's the same for both polarizations, and you might be able to do a better job if you could average it or use the crosshand polarization data. And we don't support any of that somehow. At the moment, we don't support any ways of combining the polarizations. You have to do the two independently. As Mark has told you, there is some syntax which he has shown you that allows you to handle arrays where some antenna only have one polarization and others have two polarization. It used to be that would flag all the data, and that was quite annoying. And now it doesn't do that. We can support that. We have a pole convert program was written by Eva Marti Verdal, and that allows you to convert antenna that we're observing in XY polarizations. You can convert that to left and right handed polarizations after correlation, but before you really do any other data processing. And ideally, you should arrange for that to be done at your correlation site before they hand you the data, because it's something that you really want done by support scientists. And Jive does now offer that, I believe, for EVN data where appropriate. And the CASA fringe fitter has been in active development with the Rings project. Recently, I implemented functionality that would allow you to model the dispersion term of the ionosphere in your fringe fitter data. Now that becomes important as your fractional bandwidth becomes large. That becomes important, and it's already important when you drop down to P-band observations at 300 megahertz, I think it is. And it's also crucial if we want to be able to handle low far long baseline data, which is a kind of VLBI data in a way. And we would like to be able to make CASA appropriate for data reduction there. And we have tested the fringe fitter with dispersion on low-fi data, and it works, but we're in the process of seeing how that can be fitted into the low-fi long baseline pipeline more generally. So that's happening, and development is actively ongoing. We're still working on improving the fringe fitter, and we're committed to, we have an institutional commitment that we are going to be working on the fringe fitter and continuing to develop CASA for VLBI. If you decide that CASA is a good package for you because you're familiar with it, or because for whatever reason, if you want to use CASA for VLBI, you can be secure that that will be possible for the foreseeable future, and it will continue to get better. And we offer user support. You can email people at Jive or the EVN for EVN data, and we're integrated into the NRAO's ticketing system for providing CASA support. If you have problems or questions that you need us to look at, that can be arranged through them. And again, this is a final reminder that you should always plot your data, right? Whenever you're calibrating VLBI calibration, a lot of the time you need to it's not, in many cases, it's not something that you can just have a pipeline, run it through the pipeline, and everything will be fine, and you can just go and have a cup of coffee while your machine grinds away, and you'll come back and there'll be a beautiful image ready for you. A lot of steps need to be adjusted by hand. You need to look at things, you need to inspect your data. And I've seen in earlier iterations of tutorials where we've had CASA-VLBI, sometimes things go wrong, and if you don't check, you don't know what's gone wrong. You should always plot your data after calibrating to make sure it really did what you want. And there are some, the diagnostics for that are fairly simple, so there's no reason not to do that. And I think I'm a little bit ahead of time, but I'm quite happy to stop here and we can have questions and then maybe you can have a slightly early break, because why not?
Thanks, Des. That's always good to be ahead of time than later on. Has anyone got any questions? I will pass it over to Mark, who will be collating them.
Indeed. Well, we're getting quite a few of them, so maybe we'll fill some of the time that there's left over. So the first question is, how is the signal to noise ratio of the fringe fitting solutions calculated in CASA?
Right, now the answer is as far as possible in the same way as it was done in APES. So you know, the theoretical justification for that is perhaps not entirely clear to me, but as far as possible, I looked at the original code from APES and reproduced it, so that if you have an intuition about what you think is good based on APES measurements, then that intuition should be transferable to CASA. Obviously, I'd like to have an a priori answer of exactly what that should be mathematically, but this is what we have instead for now.
I hope that answers the question to whoever asked it. The next one is, how is the fringe fitting done across the wide bands, for instance, SX band you mentioned, in particular ionosphere and source structure causing large phase variations across the wide band? I think you mostly answered this, but you might want...
I mean, I can repeat and maybe elaborate. You just take your phase data across the spectral, you know, as a function of frequency, and you just put it all onto one big frequency grid and take the Fourier transform, and then, you know, for the Fourier transform stage, and then once you've got that estimate, you put it into the global fringe fitter, which can trivially use all the model and fit the difference. And, you know, you might be worried that the assumption that your delay and rate are, you know, completely characterize the phase across the band may not be true, and you might be right to have that concern, but the fringe fitter will do its very best to give you the best estimates of delay and fringe rate, assuming those things are true. And if you're lucky, I mean, we've tried it on SX data and it seems to work okay. It's not been, it's not in production in any SX based instrument that I know of, but, you know, we'll, if it turns out that there are better things to do, then we'll look into that. But at the moment, it seems to be okay.
And then the next question is the global fringe fitting significantly better than the baseline-based approach?
Well, I would be happy to pass that question on to Benito if you would like it, but the folklore suggests that it is, yes. I mean, you're using all the data instead of just some of the data, right?
Yeah, exactly. So you basically win by square root of the number of subbands that you have. So that's the main improvement that you have. If you really get good solution from the beginning, you may not see any significant differences from one to the other. But on the cases where you have signal to noises of around 10 or 7, then it may do a huge improvement from one to the other.
Yeah, this of course ties in with the somewhat controversy between, especially in high frequency VLBI, the school of Hobbes and the school of Apes, where the problem with a baseline-based approach is, of course, that if you're not careful, you're introducing closure errors, because you're maybe applying phase corrections, which should be largely station-based, but you might apply a different phase correction on different baselines to the same station. So, and that would affect the final outcome of your science. So that's not a good thing. So a purely baseline-based approach can't really work. You always have to reconcile what you find there and apply it correctly before you can do any imaging. Okay. Next question is, what was changed in plotting or calibration application to get from the right-hand panel of slide 10 to the left-hand panel of slide 11? That's a very...
Slide 11 doesn't have any plots on my screen. So is it, are we talking about these two? Is it, I'm still sharing the screen, right?
Yes, you are.
So we're talking about this slide?
Yes, I suppose so.
Okay. Right, so the left-hand side is after the manual phase cal, but before the multiband, and the right-hand side is the same data after the multiband fringe fit.
Sorry, Des, can you repeat that?
I can. The left-hand side is after you've done the manual phase cal, so your phases are now aligned across the bands, but there's still residual slopes. And you're looking at a different scan from the one you used for the manual phase cal. The right-hand side is after you've solved for the multiband fringe fit and applied the corrections.
Okay, yes, I've got that.
So this is you know, this is a site you're on the way. On the left, you've got all your phases aligned, but they're still not flat and not at zero. And the right hand side is, you know, this is what you want to see when you've finished fringe fitting. This is what you should see on your calibrator source.
So the next question is, assume we have a strong enough target source, so no need for a separate calibrator. First, one usually implicitly uses a point source model for the fringe fitting. Then one calibrates images and self-calibrates and finally comes up with a source model. Could one get any benefits from rerunning the initial fringe fitting with this derived model of the source?
Well, I think the answer to that is yes. And in self-calibration, surely applying the model and then redoing the fringe fit is one of the steps of that can be used in self-calibration.
Okay, and then the next question, is there a covariance between time and frequency variation of the phase so that fringe fitting needs to take into account?
Well, I mean, what we've done here is we've modeled the phase as a first order Taylor's expansion of delay and rate, time and frequency. And of course you can have higher order terms, and you know, you're just fitting a linear model and hoping for the best, and that is usually good enough. But while the in frequencies across the frequency axis, right, the frequency when you have a slope in the frequency axis, that corresponds to a physical delay, and that's really a real physical phenomenon, and you expect there to be a true answer there in a sense. In the time dimension, you're really just doing a first order Taylor series and saying, well, look, everything's locally linear. That's the whole point of Taylor series. And it's completely true that mathematically, as you make your intervals in time or frequency larger, then that model will start to show signs of strain. But the question is, do you have enough information to do a better job? And is it useful to try and fit higher order terms in a Taylor series or a more sophisticated model? And so far, there hasn't really been anyone who's made a compelling claim that there is. So what we tend to do instead is we tend to look at other effects, physical effects like dispersion that we know we can characterize, and we try to kind of look for those in the data instead of just expanding the Taylor series to higher order terms and seeing what happens.
Okay, and then there's a last question, which says, could you please elaborate on using FFT mode method for initial guess?
Well, the point is with, I guess, I can elaborate in various different ways. I guess this is the plot that shows you, you know, when you take raw data and do the two-dimensional FFT, you get a good result, right? And that's essentially, you know, if you're fitting a linear model and you could do it globally, then you might say, well, what's the added value of doing an FFT stage first? The main reason is that you're working in phase, right? Phase is circular, and that means that you have ambiguities. If you're looking for a straight line in non-phase type data, then you wouldn't necessarily need to do a Fourier transform. I mean, you're really trying to fit a straight line to a bunch of points, and you might say a Fourier transform is a kind of roundabout way of doing that. But the problem is you can fit lots of straight lines because they can wrap. And the Fourier transform kind of allows you to pick a nice one that you know will be near a value where you can reasonably expect a global method to converge without getting lost in the possible ambiguities. So for a lot, I mean, for a lot of purposes, if you have really good data, you can do as Benito has said, you could do the Fourier transform method, and you wouldn't even need to refine it; it would be good enough. But if you want to use all the data and all the baselines, you're faced with the problem of how would you integrate all the different baseline estimates of the delays and rate, and then you don't. You move instead to a model where you have an antenna-based model that where each antenna is modeled in all of its different baselines, but you use the same model on a per antenna basis, and then you can fit all the data, and then you can incorporate all the data and do a better job. So, the Fourier method is a useful and helpful bootstrap that allows you to then do as few possible allows the global method to converge fast. Is that enough elaboration, do you think?
I hope so.
We've got one question from Amy. I think it's from the previous question before, because the slide numbers are actually different with the online one and this one. So I'll put Amy through, and it might be easier for her to explain. So you should be allowed to chat now, Amy.
Yes, can you hear me?
Yes,
yeah,
I can.
We can.
Great, yeah, so I was using the PDF numbering. So it looks like what I actually should have referred to as slide 9 and slide 10, as you have them labeled. Yeah, so.
Oh, I see what you mean, okay. So on the left of the slide, you have the, which you didn't ask, I think, but the left of the slide is your data before the manual phase calibration procedure, and the right of it is after the manual phase calibration. So you've done, this is all on your bright calibrator. Okay, so this is where you've done the fringe fit independently for each spectral window, and you've established that on the data that you originally fringe fitted, it's taken out all the phase variation. It's now completely flat. Okay, then you apply that calibration to the whole data set, and you look at another stretch of data, and that's what you have on the left here of this slide. This is a question, right?
Yes, okay, so it's maybe different scans.
But this is a different source.
Okay.
Looking through a different part of the sky at a different time, and you see there are now again slopes corresponding to delays that you haven't completely eliminated. But the point is that they're now all aligned across band, so that when you do it, you will be able to use all the data in one go.
Great, thanks very much.
Okay.
Great. Is there any more questions, Mark? I can't see any myself.
Not that I can see.
Okay, well, if there isn't any more questions, we might as well. Well, thanks again, Des and Benito, for the lectures this morning, and thanks everyone for their participation. I've learned some stuff as well. I didn't know some of these things were implemented yet. So we should probably take an early break, and then if anyone else has any other questions, drop them onto the Mattermost. So the next thing we're going to do will be the data processing B. It's going to be back in the plenary, but we're not going to use the breakout rooms, I think, Ilse, if that's right.
No, that's the plan. So the breakout rooms were not a big success yesterday. It was too much work to get everybody in. So we'll do the plenary, and what I will try to do is have the breakout rooms activated. So when people have a question, the tutors can have a one-on-one or several people with a similar question in one room. This depends on the functionality. The co-hosts can also move the participants, but this is at least it's optional at this point, and otherwise all the questions can go through the Mattermost chats and everything. It seems to be working very well for the lectures at least, so let's keep that up and running. So we're going to close this session in a bit and move to the plenary session. I don't have the exact time in my head.
It should be 11 UT.
11 UT, yep, that sounds about right. So we have a bit of a break, a coffee break, tea break, beer break, whatever your time zone is and your poison of choice. And we'll see you at 11 UT in the next link. I'll post it in the Mattermost general channel as well. For the people having problem with their audio, the next session will not be live streamed, but should you have any issues, we can always switch that on. So if you want, just let us know in the chat or in the Mattermost. We can switch on the live stream to YouTube if that's any better for you. And we'll see you in a little bit under 45 minutes.
Take care, everyone.
I copied all the questions and answers from the Q&A, I think so.
Okay, thanks.
We can close the session whenever we want.
Good. We'll kick everybody out.